Welcome back, class. Let's take a look at buoyancy and just some very basic dynamics about this concept. I have a more detailed video in a different lesson that I'll link to at the end of the video, or you can find it in the playlist for this topic. So let's just jump in. We're all familiar with Archimedes. We've at least heard of him. A mathematician, and he's that famous guy from years back, way back, that had that aha eureka moment and supposedly ran down the streets yelling eureka as he came across the whole concept of displacement. So like how fluids are displaced by the volume of an object. So this is something that you saw in a very basic chemistry class, where you realize that volume of water displaced by an object helped you to figure out some dynamics about density and things of that nature, right? So we can use that here as well to sort of illustrate Archimedes' principle. So with that said, what we want to do is let's just try to visualize this. Let's just let that represent a water line. So you've got the top of the water. So here's up here is above water. Here is below the water line. Okay. So if you have an object that is suspended in that, and of course it would be a three-dimensional object, so this is just a square. So I'm just saying it's suspended in there. We do know that obviously there would be some pressure in multiple directions. We're going to assume that this object is not moving left or right. And so for the purpose of this concept here, we know that we have our x and we have our y coordinate planes. We are assuming that there is no movement along the x-axis, and we're just focusing on the y-axis right here, okay? So with that said, there's the concept of forces, knowing that they occur in pairs. So our net force is going to be equal to the sum of the forces acting on this object. Well, let's think about this. We know that if it's right, the way this is drawn, that there would be some mass of water above this, and we know that water would also be pushing up on this object. Now, there's also forces on all these sides pushing, right? Now, since it's not moving left or right, again, we're assuming that those forces along what we're defining as x, we're assuming that they're equal on both sides, and so we're ignoring that for this lesson right here. Okay, so if it were moving left or right while submerged, then of course we would take a look at that. Just for a basic concept of buoyancy, we're ignoring that for right now. All right, so if you think about it, when we submerge this object, there would be a downward force that would have to be due to gravity. And then there would also be some upward force that we would call the buoyant force. Okay, so that's F with a capital B. And it normally is written as a capital B. Occasionally, sometimes, you might see a lowercase b written as well. But I'm going to try to be consistent where I'll write a capital B, just because it's what I most predominantly have seen, and I just don't want to confuse you. In physics, there tends to be a whole lot of letters, and unfortunately multiple ways that people tend to write the exact same concept. I'm going to try to stay focused for you. Okay, so understanding that, we would say that the net force acting on this object would be the buoyant force plus the downward acceleration due to gravity, right? That makes sense. Now, acceleration due to gravity, that is downward, so we know that that's a negative force. So remember that wherever we have acceleration due to gravity, that we're going to be dealing with a negative value in some way, right? We still know that this is mass times acceleration right here, right? And that doesn't change. As far as the buoyant force goes, that we're going to be looking at the pressures that are involved with the fluids involved, And we'll have to also sometimes deal with things like surface area and things of that nature. Right here, what we're doing is looking at a basic concept that if we have net force and we have buoyant force plus the force due to gravity, that tells us something about how buoyant the object is. Well, let's think about this. If we've got all right, let me draw a better water line. So we've got a water line. Okay. And let's just say the object was, I'm just going to kind of do something down here. Or let's just say that part of the object is above the water line, and then other times the object seems to continue to keep falling. Well, if it's here, this one in the middle, we're going to assume, we can assume that this one is what we would call neutrally buoyant. Buoyant is one of those really fun words, buoyant. Up here, we can say that this one has it is positively buoyant, and down here we could say that this is negatively buoyant. And the reason for that is if the force due to gravity is greater than the total force upwards, then it would have to continue to sink. So it makes sense that we'd have negative buoyancy. If by chance it goes below the waterline and it just sort of stays in one place, so to speak, for the most part, the average region of space it stays, we're going to assume the water is not moving, that the water is completely still, then we would say this thing is neutrally buoyant. That would mean an equal amount of force upward and downward. And if it's positively buoyant, then that means there must be a greater upward force, in this case being the buoyant force, right? And that's what's pushing it above the waterline. It's enough force to push it above, and so it would have a greater overall net force, right? Or the net force would have to be positive in that case, right? So let's just go take a look at a little bit of a problem. All right, so our object weighs 11.4 newtons. So let's just get the object out there. There's the object. All right, let me try this again. We'll just go with that. All right. It weighs 11.4 newtons. Now, what you need to remember is that a weight is a force. Weight is a force. Okay, mass and weight are actually two different things. They tend to be used interchangeably, but by now, if you're in this course, you should always remember that when we hear the word weight, we are talking about a force. Okay, so the object weighs 11.4 newtons. That's just a statement that says wherever this object is, it doesn't matter where it is, that it has that much force, which means that is its downward force due to gravity. So we can assign that a negative 11.4 newtons. Okay. When it's submerged in water, it weighs 8.77 newtons. So when submerged in water, it has this. So what that means is if it's submerged in water, that there is a buoyant force pushing it up, and then you were to look at the scale measuring it and you go, okay, well, it went from 11.4, and your scale is going to show positive, but we would know to write it as negative because it's being pulled downward. Now we look at the scale and we see 8.77. Well, that lets us know that we have a net force of 8.77 newtons, and we can still assume that that net force is downward, all right, because it's saying when submerged in the water, it weighs this. If the value, if the upward force were greater, then it wouldn't still have a value that is greater than 0 on the scale. It's still showing that there's a downward force of 8.77. That's how we can interpret that. All right, so we go back to our basic concept. Okay, and so right here, what we can do is figure out what it is our buoyant force. So if we rearrange this equation, we know our buoyant force would be the net force minus our force due to gravity. So we know our net force is a negative let me rewrite that, 8.77 newtons. That would be minus our force due to gravity, which is let me fix that for you, a negative 11.4 newtons. All right, so we know that's effectively going to add that right there, right? So we've got, let me get my calculator. So we've got a negative 8.77 plus 11.4. That gives us 2.63 newtons. Okay, so our buoyant force we know is 2.63 newtons. So there is an upward force. So the buoyant force is an upward force. All right, it is an upward force. So let's think about this. I mean, that makes sense that it just be the difference between the 8.77 and 11.4. Because if the buoyant force is only pushing up with 2.63, that's not enough to push this thing higher up above the water line. This thing is going to continue to sink. It is negatively buoyant. All right. So pretty simple, straightforward process. And of course, you would go about measuring your forces in a lab situation the way you would. You would have to get mass, because remember that force is mass times acceleration. So you still need to know the mass of the object, et cetera, et cetera, et cetera. Well, right here it says, what's the mass of the object? Well, let's figure that out. All right. So let me just draw a little dividing line here so we can do this. So we've got force equals mass times acceleration. Well, what we really got is the force due to gravity times mass times acceleration due to gravity, right? And if we rearrange this equation, we get mass equals this downward force divided by our acceleration. Well, the downward force is a negative 11.4. That's kilogram meters per second squared. We're going to divide this out by the negative 9.81 meters per second squared. You should see that meters per second squared cancels out. We're left with just kilograms. This is a wonderful thing. All right. So get to our calculator. Clear that out. We've got 11.4 divided by 9.81. That leaves us, let me put this over here. So our mass is, let me erase this so it's all together. All right. So mass equals 1.1620. There's like a whole bunch of numbers. Okay, and that's obviously kilograms. So we're left with about approximately 1.16 kilograms. Okay, 1.16. All right, that's the mass of our object. All right. Now, if we think about this, let's go back to this concept here. I just want to leave you with this thought that if we're talking about the buoyant force, all right, the buoyant force, if you think about how we rewrote this, let's think about how we rewrote this right here. The net force was the weight of the object when it was in the water, all right? And essentially what we ended up having to do was subtracting the weight of the object out of the water, okay? And in future, and whether or not it's future or past, depending on the order you watch these videos, we know that work is force times distance. So don't confuse this right here, the capital W on one versus the other. So I just wanted to draw your attention to that. So if you've already seen a capital W before, that you're not confusing that. They obviously are related because work is equivalent. It's equal to force times distance. And when you're doing work is energy. We can equate the buoyant force. We can equate this to energy, and we will in later lessons. But I just wanted to bring to your attention that this right here is a concept that is what we have highlighted right there. Okay, so it's just very simple stuff. It's fairly intuitive. I just wanted to draw your attention to all this. Good learning with you. Stay curious. I will see you in another lesson real soon. Take care. Bye.